Welcome to my tutorial. We'll be going through some different data types in programming today. We will first start at stacks, then move on to sets, and then finally finish with trees. So let's get started. A stack is a linear structure that stores items in a last in, first out, or first in, last out manner. In stack, a new element is added at one end and an element is removed from that end only. The insert and delete operations are often called push and pop. So in Python, we use lists as stacks. It doesn't actually come with the built-in stack uh, data type, and so we use the lists to simulate what a stack would do. And so we have a couple different frequent stack operations that are in most languages. You've got push, pop, size, and empty. And so to do these operations in Python, we use for push, we do myStack.append, so your .append is your push. Pop still exists, and so you can do myStack.pop. Size, you just do length of myStack, and then to check if it's empty, you just check if the length of your stack is 0, and then we'll check if it's empty. So to create a stack, it's just the same as creating a list, basically. But instead, you only append things to the end, and you only pop things from the end when you want to remove them. So you kind of set those boundaries for yourself. Python won't really mind if you try to do it another way, but if you want to use it as a stack, that's what you have to do. So to remove from a stack, you do mylist.pop, as we've seen earlier, and if you want to remove all the elements, then you just go through each element and then pop. So you can do that. Pop, actually, I had to search because I wasn't sure where the term pop came from, and so when they were first teaching the idea of a stack, they used the analogy of, if you've ever washed dishes, like in a commercial restaurant or something, they have that ginormous pile of dishes, and they're like spring-loaded, and so you would push the dish on top, like so the plate would go on top, you push it down, or you would pop it off, and so like you would actually like pull it out and it would make, I guess, kind of a popping noise, or the spring would make a popping noise, and that's why they call it pop. So to print from a stack, you can pop all of the elements. That will remove them, however, and so remember, you can only access the last element no matter what it is, and that gives a stack some of its charm and some of its use. However, it also makes it a little bit restricting, which can be good if it's restricting you in the right way. So let's create a task tracker, very simple. We'll put things from beginning to end, right? We'll push them all in. So we'll create our task tracker as a list or a stack that we are now going to use as a stack, and then you just append your tasks to them, a bunch of them, right? And then we just check what our current task is. We print the last task we put in, because that's the one we're able to access in a stack, right? And then as soon as we finish it, we can just pop the stack out. So we put that together. We've got a really basic task tracker, but remember, you can only go from back to front. So now that you've put them in, you'd have to vacuum the living room first, then make the bed, then clean the bedroom, then wash the dishes. So it is ordered. It won't allow you to jump around to different ones. You have to go in order as well. So your turn. All right, let's have you create a stack that will keep track of a number of pancakes on a plate. Here are your requirements. You have to be able to get the user's input, add pancakes to the stack, remove pancakes from the stack, and then get the number of pancakes. Also, don't let the user error out when he tries to get a pancake, but there are no pancakes. So I will give you time to do that. If you want to pause the video, you can go do that right now. Otherwise, we'll go straight to the answer. Okay, so here is the solution I worked out. Yours might be different, and that's okay. So first, we set our play to true so that we can have our while loop just go through the inputs and handle our pancakes. So first, we'll get our command. We'll figure out what the person wants to do. So if they want to append a pancake, you say A. There you go, and then you would append pancake. Command E, if they want to eat a pancake, then you would just pop off a pancake and get rid of a pancake. But if there are no more pancakes, then you tell them, hey, there are no pancakes left to eat. If they want to get the number of pancakes, then and they say N, then you just print the length of the pancakes. And if they want to quit, you just set play to false, and then we won't keep looping through. If they do anything other than A, E, N, or Q, then we just want to print invalid input. Please specify either an A, an E, or an N. Okay. All right, so let's go back. You scroll to the top, you have a back button. Cool. Now let's go on to sets. So sets are data structures that lack order and don't allow duplicates. Sets positions are hashed, which means that we can draw from a set at O1 performance, which is just about as good as you can expect. And so we have some common set operations. We've got our member, size, add, remove. So member checks if the value is in the member of the set, and you can do this in Python by saying if value is in my set, and that's O1 performance. All of these will be. Size, you just check length of my set. Add, to add a value to your set, just say my set.add. Remove a value, you have my set.remove. So why would you use a set? It's because they have really fast performance for adding, removing, and then finding members. Or if you need to find unique values in data, you can do sets, and then store values that need to be accessed quickly. You would not want to use a set if you want to keep track of how many times a value pops up inside of a data set, because it'll shrink it all down and each data set will only have one representation in your set, or each data value will only have one representation in the set. So sets use a technique called hashing to decide where to put the data in memory. So using hashing, sets can know where a value should be in a set. This allows for O1 lookup times as well as O1 performance for adding and removing. So this is how sets work basically. You get your value, right? You run it through whatever your hashing algorithm is, and it'll return to you an index for where you should put it. So in this case, it'll give us 12. We'll put hello in 12. Hashing can be complicated to understand, but let's give you an example. Let's say we had some people in a race and we wanted to keep track of them and then make it so we could look them up later. And one way we could do this is just by giving each of them a number when they walked into the race, and that'd be like indexing. But if we want to look up someone faster, we need to go through, or if we wanted to look someone up that way, we need to go through the list one by one and see if any of the names matched the people we are looking for. So how could we solve this problem with hashing? Well, let's create our algorithm. So our algorithm will be, for this race, the color of shorts plus the first name plus the last name. Now, when we look for someone, we start searching in the colored shorts section, then we find their first name, and then we look for their last name. So if we found out that we had more than one John Smith with red shorts, then we can chain it, is what it's called. So then we have a very small list to go through. So we have 1, 2, 3 John Smiths, and then they can decide which one's them instead of having to go through the entire list and then finding them. Okay, so creating set functions, or set functions. Sets have certain functions built into Python. One of them is intersection. So if we were to do min for seats in cars, we wanted to find a car with AC and a minimum of 4 seats, we could do an intersection and find only those cars that have both values or in both sets. Or let's do a union. So we want to find one that has AC or a minimum of 4 seats. And so we would do a union there, and that would return the sets, or a new data set that has both of these from the 2 data sets that we put in. So let's go. So let's get your question for this, your problem for this assignment would be to create a new program. It's going to be get the occupied movie theater seats. So let's say you work at a movie theater and you keep running into the issue that theater seats are being given out to more than one person. How could you solve this problem using a set? And I'll allow you to define your own problems with this one, and we'll see if it works. Okay, you can pause the video now, but we'll move on to the answer. All right, so this is how I did it. First, we create our set of occupied seats. And so we can add seats, give them a seat code, and then if the seat is in there, we return that it's taken, else we just add it and tell them their seat's been saved. And then we get seats, we can print every seat, and then for seat and occupied seats, we just print it. And then while this is true, this is where we get our input. So A, if they add seats, G, if they want to get seats, and then if there is an invalid command, we print that. All right, let's move on to topic 3. Trees. Okay, trees are linked lists that are full of nodes which we connect with references to the node's pointers. Trees can connect to multiple different lists, unlike linked lists, or multiple different nodes, unlike linked lists. So why would you use trees? Trees have really good performance when you're searching for new material or when you're storing material. And trees that are balanced exhibit O log n performance. Trees can allow us to store more data at quick speeds. One type of tree is a binary tree, and a binary tree is a tree with which each parent node has a max of 2 kid nodes. So we can only give you a picture right here. This is a binary tree. Each tree node has two, or each parent node, or not each parent node, but a parent node has a max of 2 kid nodes, and it cannot have 3, it cannot have 4, it can only have 2 or 1. Or I guess 0 as well if it's a leaf. So some useful definitions. A parent node is a node that links 2 other nodes, so this would be a parent node. A root node is the beginning of a tree, so that would be a root node as well. And then a child node is a node that is linked to by a parent node, so these are child nodes, all of the ones that come after that. A leaf node is a node that doesn't link to any nodes, and each node to the left or the right of the parent node forms a subtree. So this would be a subtree, that would be a subtree, and then each of these are also parents. This is a parent, and then these are leaves because they don't connect to anything below them. So let's go through some common binary search tree operations. We have insert, which inserts a value into the tree, remove, which removes a value from the tree, contains, which checks if the tree, or returns true if the value is in the tree, traverse forward, visits objects from smallest to largest, so they'd go 5, 6, 7, 9, 12, 15, 19, like that. Then we have traverse reverse, which would go in the opposite order, and then height, size, and empty checks if the root node has no children. So in binary trees, you can have balanced trees or unbalanced trees. An unbalanced tree is just a list that, or it's basically just a linked list. It doesn't give you any of the performance boost of having a binary tree because you have to go through each element to find the element that comes next. And so when we have a binary tree, we get O log n. When we have a linked list, it is not that quick. It is not an O log n. So first, let's go through and make a basic implementation of a binary tree. This allows us to insert values and then print the order of those values. I'll let you look through this one on your own and check out the different parts. I did leave some comments so you can find or read through the logic if you'd like. And so there's that. I have it printing. It'll print out all of the objects, all of the values in the tree, and they'll go from left to right. So basically you're traversing the tree and then finding, let's see, reverse traverse, or yeah, you would be traversing forward because it goes from smallest to largest and prints it out that way. So using this binary tree we implemented above, create a function that can search if an element is in the tree. Okay, if you'd like to give that an attempt on your own, go ahead. I'm going to click on the answer now in 3, 2, 1. Okay, all right, so this is actually fairly simple. This is the way I've done it. So first we check if the self root is none, then we just return false because there's no values in the tree and we don't want to throw an error, right? And else we return this self._exists, self.root data, and we call this recursive function here. So then we check, so if the node.data equals the data, then hey, we found our node, let's return true. Else we see, is the node.data greater than data? In which case we want to search to the left. We don't need to search to the right because it won't be on that side. And if node.data is less than data, we'll search to the right because it won't be on the left. And then that will return either true if it's in there, or it'll return false if it's not. Okay, all right, that is what we've got so far. Feel free to send me any questions you might have, and I hope you have a good rest of the day.